So we're looking at total probability. Okay, so remember that we just gone through conditional probability. Alright, so this is a second question. So a fair coin is tossed twice. Find the probability that two heads appear, assuming that the first appearance is a toss, that the first appearance in the toss is a head. Okay, and then the second one is there is at least one head in, or the head appearing. So look at this. For I, the given is that the first appearance is a head. Okay, so you are looking for probability that two heads appear. So you have to know the sample space and then bring out those two events. So the first event is to, now the sample space is HH, HT, TH, TT. Alright. Now so you have to bring out this event. Two heads appear. Alright, so two heads appear. Just look at that. This is only the element. This is only the event. So two heads appearing is HH. Alright. So that is kind of A. Then the given, which is saying that the first appearance in the toss is a head. So the first appearance is a head is this and that. So the first appearance is a head is that, and that is also B. So you are looking for probability that B has happened, given that A will happen, is the intersection. So you have to find the intersection of this and that, and then the intersection of this and that is HH. Alright, and then probability of B. So remember, HH is coming from the sample space where each of the elements has a probability of 1/4. So the probability of HH is just 1/4, which is the intersection, 1/4. Probability of HH, HT is 1/4 plus 1/4, okay, which is 2/4, and that gives you 1/2, okay. So the second one too, this remains the same, the A remains the same, but the B changes. There is at least one head appearing, so at least one, so you can have a more there. So there's one head, there's one head, there's one head. So I think in a B you have 1, 2, 3 elements. So you have 3 elements in the B. The intersection is still HH, so that probability is 1/4, but the B has now changed to 1/4 plus 1/4 plus 1/4, which is 3/4. So 1/4 over 3/4, and that gives you 1/3. Okay, all right. So the total probability is the next thing we have to look at. Okay. So suppose that the sample space S is partitioned into mutually exclusive events. So let B be the other event in X intersecting with all the n elements. Right. Then we have that. So what we are saying is that, let me sketch total probability. What we are saying is that we have a set and this set has been partitioned. Okay, this set has been partitioned into, let's say, this 4 sets. 1, so you can call this as A1, A2, A3, A4, so now these are partitions, they are mutually exclusive. So it means this doesn't intersect with this doesn't, so there is no intersection. Okay, this doesn't intersect with that, so there is mutually exclusive. So this is a sample space S. Okay, so we say that S has been divided into partitioned into mutually exclusive events A1 up to AN, and we are saying that let B be any other event that is intersecting with O. So B can be something like that. So B can be something like that. So this is B. And remember that this B is intersecting with every element. Okay, this B is intersecting with every element. Alright. So what we are saying is that then we have B. Remember B is an intersection of S and B. Alright. So when you take S is a union. Remember, S is the whole, when union A1, A2 up to A4, that will be X, because it is X that has been divided as A1, A2, A2. So when you find the union, you still get back S. Okay. So when you take S intersection B, you still get back B, because it's only B that intersects with X. Okay. Right. So now we have S intersection B, and that will give us A1 union A2 up to A4 intersection B. Right. And then because these are piecewise these are mutually exclusive. Okay, these are mutually exclusive. We send this through. Okay, let's send it through. So A1 intersection B union A2 intersection B. All right, in that order. All right. So remember, where A1 intersection B are also mutually exclusive events, then probability of B is the probability of this. No, so you know this is B, so you take a probability, you just apply probability on this, and you take probability through this. All right. So probability of B will just be probability of this one. So the union tends to plus up to the last one. Okay. All right. And then remember that with this, when you go into the Bayesian, you go into the conditional probability. We said that probability of A happening given that B has happened, we said this is equal to probability of A intersection B divided by probability of B. Alright. So what this means is that if I want to find probability of A intersection B, probability of A intersection B is equal to probability of B times probability of A given B. Alright, so just cross multiply, and this gives you that. So remember that in this set we have what we just did as, okay, S, what is S? S we said is a partition, so S is the union of A1, A2 up to AN. Okay, so we just multiply, kind of take it through. So A1 intersection B, A2 intersection B, in that order. So when we apply probability here, probability to B, when we apply probability to B, we apply same probability here. Okay, apply probability here to the whole of this guy, and then applying the probability, we'll turn this to plus. Okay, so we just have probability of A1 intersection B plus probability of A2 intersection B. This is B. All right, this is a mistake. So plus dot 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 plus probability of AN intersection B. All right, and remember from this we are saying that probability of A1 intersection B, we have probability of A intersection B is given as B. So if I put A1 here, if I put A1 here, then means A1 will be here, isn't it? So probability of A1 intersection B is going to give us probability of yeah, so this kind of a reverse version. Okay, so if this was a B, right, if this was a B and this was A1 A, then the whole thing would change to this. Okay, the whole thing would change to this, and then this one too will change to this in that order. All right, so if you have probability of B, which is the intersection of the particular element that intersects with all of that, and that would be the summation, this given by this summation. Okay, all right. So whatever that has happened, which is the total probability rule for finding probability of B, which is the total probability rule for finding that. So in general, the general form of this rule is called the Bayes theorem. The Bayes theorem. Right. So this is the Bayes theorem. This is the Bayes theorem. So this is the Bayes theorem. All right. So it happens that the Bayes theorem is saying, okay, there is a certain A, okay, and A is a partition of A has been partitioned into EIs. Okay, so A has been partitioned into EIs. So if you want to find the probability that A has happened, given that EI is happening, all right, then you want to find out the total probability, which is the denominator, and then the probability associated with one of the EIs. Right? Okay. So that is that. There are lots of questions here. Just try them. Okay. When you find any, go through the solution. If you don't understand any, you just let me know in the comment section. Okay. All right. So these are all examples on the Bayesian. Alright. So these are all examples on that. A lot of them for you to try. Check them out and then let's see what we can do to help. Alright, so that ends it.